Hello, third BTech EC students. Good morning. Yesterday, we have discussed about the AC electric resistance welding systems. As in the block diagram, of AC electric resistance welding system. Please note down the block diagram again clearly, so that it is a very important question coming in the end examinations. So please note down the block diagram. The block diagram consists of input 230 volts 50 Hz power supply, power transformer, step up transformer. It is 230 volts to 600 volts step up. There is circuit breaker. Next is line contactor. On the top there is a well timer. The line contactor is connected to primary of welding transformer, which is step down transformer. And then welding assembly is there, because secondary of welding transformer is connected to welding electrodes 1 and 2, and between electrodes there are workpieces to be welded are there. Okay, please note down the diagram clearly, because the diagram is always asked in the end examination. Okay, again I am repeating, it is the input power supply 230 volts 50 Hz power supply, power transformer, step up transformer, next circuit breaker, next line contactor, then on the top there is weld timer, then welding transformer, step down transformer. The secondary of the transformer is connected to welding electrodes 1 and 2. Between welding electrodes there are work pieces, metal pieces are there which are to be welded. Now we will discuss about the main parts. Power transformer. Power transformer produces 600 volts, 200 ampere power to the machine, that is the welding transformer, through circuit breaker and line contactor. Power transformer, it produces output 600 volts, 200 amperes power to the machine, welding machine. That is actually nothing but welding transformer, through circuit breaker and line contactor. The second part is circuit breaker. It is used to switch off power in case of overloading or some other problem. Then third is line contactor. It is used to connect AC power supply to primary of welding transformer only during welding time. So line contactor, it is used to connect AC power supply through the power transformer and circuit breaker to the primary of welding transformer only during welding time. So the output of line contactor is connected to primary of welding transformer. Okay, it is connected only during welding time. Okay, the timer will be on at that time. Number 4, welding transformer. It is a step down transformer. It has only one turn of secondary thick conductor connected to welding electrodes 1 and 2, through which current flows. Okay. The secondary voltage of welding transformer is 10 volts to 15 volts. Secondary current is 100 amperes to 1000 amperes. Okay, 100 amperes to 1000. It is not 100, it is 100 amperes to 1000 amperes. Okay, there is a correction here. 100 to 1000 amperes. Okay. Secondary current is 100 amperes to 1000 amperes. Weld timer, it is used to control welding time, TW. So welding assembly, 6 is main last one, welding assembly. We have again shown this welding assembly, water cooling of welding electrodes. You can note down this diagram. It consists of welding electrode 1 and 2, top and bottom, 2 workpieces, and provision for water flow, and weld spot is given, water cooling of welding electrodes. Because a lot of heat is generated, the welding electrodes become very hot. They may be welded to the metal sheets. So to prevent that, they are cooled down. To prevent welding of electrodes to metal sheets, water cooling is arranged. Okay? To prevent welding of electrodes to metal sheets, water cooling is arranged. Maximum temperature is raised at the weld spot. Heat produced at welding electrodes is reduced by flow of water. So by properly selecting pressure on welding electrodes and weld timing TW, it is possible to spot weld metal sheets of 10 to the power of minus 3 centimeters to few centimeter thickness. We can spot weld large number of metal sheets very quickly using this spot welding method. Okay. Now I think you have understood what is this electric resistance welding. So spot welding method is shown here. That is one of the methods. There are other methods. Butt welding is steam welding, projection welding, flash welding, like that. In the last class we have discussed all the 5 types of weldings. Okay, mostly spot welding is used in number of applications. Okay, so now you can see this welding assembly, 6th main part, that is very important, where secondary of the transformer is connected to welding electrodes to give current and produce heat also. Okay, that heat is to be cooled down by means of water cooling, because otherwise the electrodes will be connected to the metal sheets. So it is very difficult to remove them unless we put water cooling system. That's why water cooling system is given. Okay, that is the arrangement. So all of you please note down this this block diagram of AC electric resistance welding system. Okay, that is very important. Almost asked in almost all end examinations. So you can explain the main parts. Okay, a power transformer, circuit breaker, line contactor, welding transformer. Then we have weld timer and welding assembly. That is how this block diagram consists of. Okay. Next, we'll go to next topic. That is what I call induction heating. Induction heating. What is induction heating? You see the diagram. Please note down the diagram. It consists of a conductor, a coil. To the coil, high frequency AC is given. Okay, the coil has some inductance, the current is flowing. Why it is called induction heating? What is induction heating? if a conductor is placed in a time-changing magnetic flux, an EMF is induced in it. Okay? Because any conductor will produce magnetic flux. The magnetic flux will induce an EMF. Okay? This induced EMF produces what we call current through the path. This current is known as eddy current. Okay? So as shown in the figure, the conductor is placed in a coil. Okay? The coil AC voltage at high frequency is given, about 500 kilohertz or something like that. Okay? So it produces magnetic flux. So an EMF is induced. This induced EMF produces a current through the path. This current is known as eddy current. Eddy current is used for heating metal pieces. This is called induction heating. Okay, induction heating is done by eddy current produced by magnetic flux. Please note down again how induction heating. What is induction heating? As shown in the diagram, conductor is placed in a coil. If a conductor is placed in a time-changing magnetic flux, that is in a coil, an EMF is induced in it. This induced EMF produces a current through the path. This current is known as eddy current. Eddy current is used for heating metal pieces. This is called induction heating. The frequency of AC source is 500 Hz, varying from 500 Hz to 500 kHz. Okay? The heat generated in conductor due to changing magnetic flux is due to eddy current loss. Okay? The heat generated in conductor due to time changing magnetic flux is due to eddy current loss. The heat is produced due to eddy current loss. Okay? In the circuit, the induced voltage induced is given by V is equal to minus d by dt n pi. It is also is equal to minus n d pi by dt, which is minus L di by dt, where n is number of turns. D pi by dt is time changing magnetic flux. L is inductance, I is induced current. Okay? There is. Skin effect. At high frequency current, current is concentrated on the outer skin of the conductor. For example, if it is 500 kilohertz, the current will not flow through the conductor inside. It flows only on the outer skin. This is known as skin effect. Okay? The current is concentrated only on the outer skin. That is called skin effect. This skin effect is extremely useful in induction heating, because induction heating is done only on the outer surface. It is called surface heating. Okay? Skin depth delta is given by 1 by 2 pi square root of mu r sigma f into 10 to the minus 9 centimeters, where mu r is relative permeability in henries per centimeter. Relative permeability in henries per centimeter. And sigma is conductivity, moles per centimeter. And frequency, F is frequency of heating current. Okay? So how much depth it goes, it depends on three factors. Relative permeability of the conductor, then sigma, conductivity of the conductor, and frequency of the heating current source. Okay? Frequency of the source. Okay? So substitute all the three, we get how much depth the heat is produced. Okay? How much depth it goes. High frequency current, it goes the depth of, that is called skin depth. So skin depth is directly connected to induction heating. Okay? Here the heat, the total power entering the metal or per square meter of the surface is given by total power entering the metal per square meter of the surface is given by, we get finally P total is 4 H naught square by sigma delta, where H naught is the magnetic field, sigma is conductivity, delta is skin depth. Okay, so total power entering the metal which produces heat per square centimeter depends, is directly proportional to H naught square, inversely proportional to sigma conductivity, and also inversely proportional to skin depth. Okay, that is the how much heat produced in the conductor we can estimate using the total power generated produced due to eddy currents. Okay, that is due to magnetic field in terms of magnetic field, conductivity, and skin depth. Okay, that's how we can calculate the amount of heat produced on the conductor due to induction heating. Okay, this is next characteristic features of induction heating. Number one, very high heating rates can be obtained. Very high heating rates can be obtained. Very high heating rates can be obtained. That is one. Number two, the metal is suitable for automatic control of temperature. The metal is suitable for automatic control of temperature. Number three, the portion of surface to be heated can be accurately controlled. We can accurately calculate and also accurately control. Number four, working conditions are pleasant near induction heaters because there are no side effects, because induction heating is concentrated only on the outer surface of the conductor. So for the manual labor, it will not affect, because there is no side effects. Number five, induction heaters can be operated by unskilled labor in industry. So we don't require any skilled labor. It can be operated by unskilled labor. Number six, the cost of heating furnace and equipment is of course high. Of course, overall efficiency is 50% in most cases. So that's why it may not be economical, because 50% of the heat produced is wasted. Number seven, the heat is concentrated near the surface of the metal. Okay, that's why there is a wastage metal piece. Hence, induction heating becomes very useful in surface heating of steel rods, etc. Surface hardening of steel rods by heating. Okay, the heat is concentrated on the surface. Number seven, it is possible to have rigid control over this surface areas to be heated. This reduces wastage of heat. Number eight, with timers, it is possible to control very closely total heat transferred to the workpiece. So we can note down what are the characteristic features of induction heating. Very high heating rates can be obtained. Number two, the method is suitable for automatic control of temperature. Number three, the portion of surface to be heated can be accurately controlled. Number four, working conditions are present near induction heaters. Number five, induction heaters can be operated by unskilled labor in industry. That is number six, the cost of heating furnace and equipment is high. Overall efficiency is 50% in most cases. It is not economical. That is of course one of the disadvantages. Number six, the heat is concentrated near the surface of metal piece. Hence induction heating becomes very useful in surface hardening of steel, etc. You want to make surface hardening. This is the best method. Number 7, it is possible to have rigid control of surface areas to be heated. It is possible to have rigid control over the surface areas to be heated. This reduces wastage of heat. With the timers, it is possible to control very closely total heat transferred to the workpiece. Okay, that's how induction heating can be effectively implemented using a timer. Okay, there is a high frequency power source for induction heating, as already told. Okay, there is a typical induction heater circuit using voltage fed inverter. You can note down this diagram. It consists of AC supply, converter, there is inductance, there is SCR, then 4 SCRs in bridge form. In between, an inductor L dash and conductor where induction heating is required. In parallel, capacitor is connected. So please note down this circuit, which consists of AC power supply input, there is a converter, then inductor in series, and across there is a SCR. There are 4 SCRs connected in bridge form. In between there is inductor L dash and induction heating rod conductor. The conductor where induction heating is required is placed there, and in parallel a capacitor is connected. Okay, that is the circuit. You can note down the waveforms also. Okay, the load current IL, thyristor current, and the thyristor voltage VL is also noted down. In induction heating equipment, if conductor is surrounded by AC heater coil, it will behave as a transformer and current will circulate in the conductor. The amount of heat will be function of flux coupled, the metal characteristics and the frequency of the source will determine the amount of heat. Okay, this is a typical induction heating circuit shown in the figure. This circuit employs voltage fed inverter. Normally, furnace coil tends to operate like a short circuit transformer. So the conductor is placed in that and hence work at low value of power factor. The load coil L dash is compensated for power factor with a series capacitance. The DC series inductor and DC parallel capacitor keeps the voltage constant. The load current IL now passes through the thyristor inverter formed by the 4 thyristors in a bridge configuration. The load voltage VL is a function of operating frequency compared to series resonant frequency F0. The frequency F0 is given by 1 by 2 pi square root of L dash C, where C is the capacitor shown with the heater coil inductance L dash. Okay, so 1 by 2 pi square root of L dash C, that determines the resonant frequency. Okay, it generates a resonant frequency that produces heat. Okay, So this is it produces high frequency, and this high frequency will produce what you call the heat is produced in the conductor because of what you call eddy currents, induced current. That's why it is called induction heating. Okay, this is one of the circuits used in the industry for number of applications. Okay, please note down this circuit diagram clearly and the waveforms. Okay, so high frequency power source for induction heating, high frequency power source. So actual circuit, okay, typical induction heating circuit using voltage fed inverter. Okay, if you are asked to draw the circuit for induction heating, okay, you can draw this diagram and give explanation. Okay, because conductor here is placed by AC heater coil. Okay, it looks like a transformer, short circuit transformer, and current will circulate in that conductor. The amount of heat is a function of flux coupled. Okay, the amount of heat produced is a function of flux, is also metal characteristics, and also on frequency. That is conductivity of the metal and our amount of flux and frequency. As already explained, the amount of heat produced depends on these three factors. These three factors: conductivity, flux, magnetic field. That is the magnetic field or magnetic flux, conductivity, and frequency. These are the three factors which determine the induction heating, the amount of heating. The amount of heating depends on flux coupled, the metal characteristics like conductivity and frequency. Okay. Okay. So this is a practical circuit used in the industry. Okay. Please note down. Those who could not note down, please again note down this. There is AC power supply, converter, there is inductor, there is SCR, separate one, parallel. There is 4 SCRs in bridge form. In between, there is induction coil L dash. There is induction heating coil, that is their conductor is placed. In parallel, there is a capacitor. Okay, that is a typical induction heating circuit. Okay. This circuit employs, of course, voltage fed inverter. It's called voltage fed inverter. Normally, furnace coil tends to operate like a short circuit transformer and hence work at a very low value of power factor. The load coil LS is compensated for power factor with capacitor. The DC series inductor and DC parallel capacitor keeps the voltage constant. The load current now passes through the thyristor inverter formed by the bridge configuration. The load voltage is a function of frequency compared to series resonant frequency F0. The F0 is given by 1 by 2 pi square root of L dash C. So that's how it operates. It is effectively used in industry for surface hardening of metal rods. Okay, that is called surface treatment of metal rods. That is what is called induction heating. Okay. Okay, thank you. We'll meet again next time.